Hello everyone, thank you for watching this video today. And in this video, we're going to talk about the radius and the interval of convergence of a power series. First, let's talk about what a power series is. Okay, so what we want to do is we want to show how an infinite polynomial function can be used as an exact expression for other elementary functions. For example, the functions f of x equals e to the x can be represented exactly by this series. We call this a power series because of its powers. For each real number x, it can be shown that the infinite series on the right converges to e to the x. So what is a power series? If x is a variable, then an infinite series of the form sum from 0 to infinity of a sub n times x to the n is called a power series. Generally, an infinite series of the form, now we're just going to change that x to the n to x minus c to the n, is called a power series centered at c, where c is some constant. So real basic here to start, state the value of which c, where each power series is centered. So real easy to start here. We're looking at our x function here, and it's x to the n, but really it's x minus 0 to the n. Therefore, c is 0. This one clearly is x plus 1 to the n, so our c value must be negative 1. This one here is x minus 1 to the n, so our c value must be 1. All right, now on to this radius and interval of convergence. Think of a power series as a function of x, like f of x equals the sum from 0 to infinity of a sub n times x minus c to the n, where the domain of f is a set of all x for which the power series converges. Determining the domain of a power series is the primary concern of this section that we're going to talk about here today. Quick note here, a power series converges at its center c because if you can see here, if we put c in for x, everything is 0 except for our first term, so it's a sub 0, which is some constant. So c is always in the domain. All right, if you look over here, there's 3 types of convergence of a power series. That's where we're going to get into the blue box down here in a second, but you can kind of see the picture here. Either at a single point, either on some interval, or the entire real number system. Okay, so that's what this box is saying here. For a power series centered at c, precisely one of the following is true. Either the series converges only at c, there exists some number r, which is greater than 0, that the series converges absolutely for x minus c less than r, and diverges for x minus c greater than r, or the series converges absolutely for all values of x. The number r is called the radius of convergence of the power series. If the series converges only at c, the radius of convergence is 0. If the series converges for all x, the radius of convergence is infinity. The set of all values for x where the power series converges is called the interval of convergence of the power series. One last thing before we start looking at some problems here. We're going to be using something called the ratio test to do this. We learned the ratio test back in topic 10.8. So here's the exact theorem from topic 10.8. We take the ratio of the n plus first term over the nth term. And if the limit as n approaches infinity is less than 1, we say it converges. If it is greater than 1, we say it diverges. And if it is exactly 1, then we say the test is inconclusive. So in summary, case 1, the limit is less than 1, it converges. The limit is greater than 1, it diverges. The limit equals 1, it's inconclusive. So finally, let's take a look at some problems today. Find the radius of convergence for each power series. All right. We're going to start here by doing our ratio test. So limit as n approaches infinity of the n plus first term over the nth term, the absolute value of all that. Okay, so now we need to do some just algebraic manipulation here. Limit as n approaches infinity, n plus 1 factorial divided by n factorial. The n factorials will cancel out, leaving us with just n plus 1. X to the n plus 1 over x to the n is the same thing as writing x to the n times x over x to the n. So then we have limit as n approaches infinity of n plus 1, those will cancel, times x. All right, now if you put infinity, well, actually before we do that, technically that x, it's technically a constant here, so we could take that out in front. And then it's limit as n approaches infinity of n plus 1. All right, now if we put infinity in for n, we would get absolute value of x times infinity plus 1, or just times infinity. Okay, so going back to our test here, if the limit is greater than 1, we say that then it would be diverging. Therefore, we can say here this diverges. So therefore, our radius of convergence would be 0. All right, because the next step in this would be to set this less than 1, which we can't do. There's nothing that's going to make that be less than 1, except, of course, for 0, our center. Question B. All right, so limit as n approaches infinity of the nth term, so 3 times x minus 2 to the n plus 1, the n plus first term, sorry, divided by the nth term, all absolute value. Okay, so remember, it's a side note here, this is x minus 2 to the n times x minus 2 to the first. So we can do some cancellation here. Limit as n approaches infinity. 3 over 3 cancels. X minus 2 to the n over x minus 2 to the n cancels. That leaves me with just absolute value of x minus 2. There's nowhere to put infinity in here. We can't put infinity in for x, so that means our answer is just absolute value of x minus 2. All right, so we want to know when that would be less than 1, because the ratio test, we want to be less than 1 in order to converge, right? So we want to know when this is less than 1. Now, there's 2 ways to do this. There's a long way and a short way. I'm going to go ahead and let you know that this long way here, we can end up doing this a little bit shorter later on. But really, if we did absolute value here, so we solve this, and then we would, let's see, add. We get x's, this series would converge between when x is 1 to 3, right? So the diameter of convergence would be 2, which means our radius of convergence is just 1. And we'll see when we start going through these a little bit more that there'll be a quicker way to find our radius once we get to this point here. Okay, part C. This one might look a little daunting, but that's okay. We'll give it our best shot. Limit as n approaches infinity of absolute value. So this negative 1 to the n plus 1, I'm going to write it down here, but we're not going to need to. I'll explain why in the next step. And then we have x to the 2 times n plus 1 over 2 times n plus 1 factorial. So that's the n plus first term divided by the nth term. But instead of writing divided by the nth term, I'm just going to multiply by the reciprocal of the nth term. It's a quick and helpful trick that can save us a lot of time in the future. And you are allowed to skip right to that. Okay. Because we're in the absolute value bars here, negative 1 to any power is going to be positive. Negative 1 to any power is going to be positive. So those two things essentially are gone. All right. Then we can start simplifying a little bit here. Limit as n approaches infinity of x to the 2n plus 2 plus 1, or x to the 2n plus 3 times 2n plus 1 factorial all over, I'm just going to switch this up a little bit, x to the 2n plus 1 times 2n plus 2 plus 1, or 2n plus 3 factorial, all under our absolute value bars. Okay, so remember that this is x to the 2n times x cubed. This is x to the 2n times x to the first. So that leaves me with x cubed over x, and then 2n plus 1 factorial over 2n plus 3 factorial. Everything's going to cancel out except 2n plus 2 and 2n plus 3 on the bottom down there. All right, so I can do one more step of simplifying before we actually take a look at this answer here. Limit, as n approaches infinity, x cubed over x is just x squared over 2n plus 2 times 2n plus 3. Okay, now, again, that x squared, technically, we can bring that out in front if we want to. And if we put infinity in for both n's, we would get absolute value of x squared over infinity, which is going to go to 0. Okay? 0, if we want 0 to be less than 1, well, 0 is always less than 1, which means this is true for all real numbers. So our radius of convergence would be infinity. All right. Next thing we're going to talk about here is endpoint convergence. It's because it converges on an interval doesn't mean that it'll converge at the endpoints of those intervals. Sometimes it'll converge at both, sometimes diverge at both, or sometimes 1 and 1. Note that for a power series whose radius of convergence is a finite number r, the theorem above says nothing about the convergence at the endpoints of the interval of convergence. Each endpoint must be tested separately for convergence or divergence. Therefore, the interval can take any one of the following 6 forms. No radius, all real numbers, or a radius where 1 or 0 or 2 of the endpoints are also convergent. So let's take a look at example 3a. Find the interval of convergence. All right, so we're going to go ahead and start the same way we started before. Limit, as n approaches infinity, of absolute value of the nth term divided by the, n plus first term divided by the nth term, so multiplying by the nth term. All right, so then some simplifying will get us x to the n plus 1 over x to the n is just x times n over n plus 1. Which again, I could think of this as absolute value of x times limit as n approaches infinity of n over n plus 1. And that, we know, would converge to 1, because this is just going to be, if you use L'Hopital's rule on that, it'd be 1 over 1. So this is going to go to absolute value of x. We want absolute value of x to be less than 1. So that is true on the interval -1 to 1. So now we got to test those endpoints of -1 and 1. Okay, so let's test -1. So we'll -1 here. All right. And we'll do x equals 1 next. So when I put -1 in, I get sum n equals 1 to infinity, -1 to the n over n. That we should recognize as an alternating harmonic series. And that one is convergent. So that right there tells us that that endpoint, I don't need this big of a line here, that endpoint will be included in our convergent interval. X equals 1. Now if I put x equals 1 in there, I get 1 to the n over n, which is 1 over n. So it's sum 1 over n, okay? That is the divergent harmonic series. So we had an alternating harmonic series that would converge, but we have a harmonic series here that's divergent. So that is not going to be included in our interval, which means our final interval of convergence, I'm going to write that as interval of convergence like that, is going to include -1, but not include 1. Or if you want to write it like this, that's fine. Okay, our next example. So we're going to start here by doing limit as n approaches infinity of the nth term, so negative 1 to the n plus 1 times x plus 1 to the n plus 1 over 2 to the n plus 1 divided by the n plus first term divided by the nth term. So 2 to the n, I think I keep saying that wrong. We're always doing the n plus first term divided by the nth term. Okay, so now doing some simplification. Again, these will cancel out because the absolute value of those will just be 1 every time. We're left with 2 to the n over 2 to the n plus 1, just going to be a 2 in our denominator. And then x plus 1 to the n plus 1 over x plus 1 to the n just leaves us with x plus 1. Okay, now there's nowhere to put infinity in for n there, so which means our answer must just be this. And we want that to be less than 1 for this to be convergent, which means the absolute value of x plus 1 must be less than 2, which means our radius of convergence would be 2. Okay, where do we start here? Our center was located at negative 1, right? So our interval convergence would go 2 to the left and 2 to the right of that, or you can do it. So there's two ways to do this. You can do, the old algebra 1 method to find your interval. Or you could think of, well, the radius is 2 and my center was negative 1, so I have to go 2 to the left of that and 2 to the right of that to get my interval. All right, so that's my interval. Now I need to figure out my endpoints. So x equals negative 3, x equals 1. If I put negative 3 into this, let's see, I would get negative 1 to the n times 4 to the n over 2 to the n. Oh, that is not 4. Negative 3 plus 1 is not 4. My apologies. Negative 3 plus 1 is negative 2 to the n. Okay. Basically, in the numerator, they're either both going to be negative or both be positive at the same time, which means we can basically get rid of those negatives. So it's going to be 1 to the n times 2 to the n. 1 to the n is just 1. So really it's 2 to the n over 2 to the n, which is just 1. All right, so really, you think of this as 1 to a power. This is a geometric series. This is a geometric series where r is equal to 1. So this is a divergent geometric series, which means we are not going to include that endpoint in our answer. For x equals 1, let's try 1 now. So negative 1 to the n, and then we get 2 to the n over 2 to the n. 2 to the n over 2 to the n cancels. I'm left with this, which is also a geometric series with r is negative 1 this time. So that's also a divergent, which means neither of our endpoints are included. So my final answer for my interval of convergence is negative 3 less than x less than 1, or negative 3 to 1. All right, number 3C. Start here by doing the same as before. We have our limit as n approaches infinity. Of our nth term divided by our n plus first term, divided by our nth term. I think I've said that every single time. N plus first divided by nth. All right, so some quick simplification here. X to the n plus 1 over x to the n leaves us with just x. And then we have n squared over n plus 1 squared. All right, so again, we can think of that x as coming out in front. So we're just left with n squared over n plus 1 squared. That, as n goes to infinity, that's just going to go to 1. Okay, that's, if you use L'Hopital's rule on that, you're going to get down to 1 there. So really, we're going to get down to absolute value of x, which we want to be less than 1. So our center here was 0. Our radius of convergence is 1. So therefore, this is our interval of convergence. Now we got to test our endpoints. To see if these work here. So if I put -1 in, I'm going to get -1 to the n over n squared. Right? -1 to the n over n squared. So -1 to the n is, you could think of this as kind of like it's a convergent p series. Right? So it's a p series because p is bigger than 1, p is 2 here. So this is a convergent p series. So that one's going to be included. For x equals 1, you're going to think of this as, we're going to put 1 in for x. So it's going to be 1 to the n over n squared. Which is going to be just 1 over n squared. I'm sorry, this is the convergent p series here. This is the alternating series, which is also convergent. This is convergent by the alternating series test. So we're going to include both of these in our endpoints. So our final answer for our interval of convergence is including -1 and 1. Or if you want to write it like this, here's your 2 answers. Okay, so we're going to stop this video here for today. We're going to do part 1 of the video ending here. And then in the next video, we'll pick up here for the last 3 slides, which is the differentiation and the integration of a power series. So come back next time to see that. Otherwise, thanks as always for stopping by, and we'll see you again real soon.